Very good afternoon to all in one present here. We are going to start the webinar, the standard model and beyond. And to start with, I request our head of the department, Professor Indrajit Sharma, and Dean, School of Physical Sciences, C.R. Bhattacharjee, Professor Sreerup Raychaudhuri from TIFR, to be there with us in the inaugural session, and I'm expecting other speakers also, but probably their connection is not sustaining. I could see Professor Rishi Khatri. I think Rishi is there. So here we go. Yeah. We formally start now. And the standard model, this program, Standard Model and Beyond, actually, I was thinking from quite a long time to organize such an event, but somehow it didn't work. And during this COVID lockdown period, we also started celebrating our silver jubilee of the department, because this academic session from July to next June is our 25th year of the department. And in connection to this, I thought of organizing this. I wrote to actually Professor Raychaudhuri, who immediately agreed and also gave me lots of suggestion in organizing this event. And then that is why we are here. And I hope this we could accommodate 6 lectures, because it is a 2-day webinar and we don't want to have too many lectures. But the main aim is to make the participants interested to pick up issues and read through and maybe work in future in the issues related to the standard model and the modifications of standard model, as well as issues. So we have 6 guests with us, guest speakers, who will speak over the 2 days. And the standard model, it doesn't need much of introduction, but as a convener, I'm supposed to give a little bit of introduction. So the standard model, it's a crown to the particle physics, and it's a really successful story in the sense that within its jurisdiction, it is extremely well behaving, extremely successful in describing the interactions as well as the particles that we are seeing around Earth, the basic building blocks. But having said that, it has lots of issues, and as you know that first and foremost major issue which everyone knows is that standard model, which is supposed to incorporate all the 4 forces of the nature, but the standard model, so-called quote-unquote standard model, it incorporates only the 3 of the forces, not the gravity. So it's a major issue how to incorporate gravity. Another issue is that with the neutrino mass, because the standard model tells you that the neutrinos are supposed to be massless, but experiment tells you that they are massive. So that is another big question. And in the cosmological realm, we have this dark matter, dark energy things which we are not sure what they are exactly. And also the matter-antimatter asymmetry, lots of issues are still there. So we really think that standard model is a low energy description of something which we would like to call a theory of everything. So definitely we need to know the full theory, that is the theory of everything, and particle physics, the research as a whole is a search for the whole full scenario rather. So we are here, we would like to hear from Professor Raychaudhuri first that, when we go for the technical session, that what the standard model is all about and what are the issues. And then we have 2 other lectures today of Professor Rajesh Gopakumar and Professor Rishi Khatri. They will discuss about the issues with gravity and as well as cosmology. Tomorrow we will have Professor Navamandal telling us from an experimentalist's point of view how to detect particles, what are the issues related to those things. Then we will have Professor Pascal Serpico, who will discuss about the dark matter issues. And then finally, we have Professor Shruvavati Goswami, who will be discussing about the neutrino issues. So before going to the technical sessions, I would like to request the Dean of Physical Sciences, Professor Chiranjan Bhattacharjee sir, to please speak a few words in this occasion. Professor Bhattacharjee, please.
Good afternoon, Professor Atri. On behalf of the School of Physical Science, esteemed speaker, in particular Professor Raychaudhuri and Professor Khatri, who are present, and all other speakers will be speaking in this international conference over the 2 days that is being hosted by the Department of Physics. The theme of the conference, I get to know, is standard model and beyond. In fact, the issues pertaining to the mass of neutrino, dark matter, antimatter, dark energy, etc., used to intrigue us very much when we are introduced to the early physics classes during our higher secondary. And I thought that these issues might have been resolved by now, but as a student of chemistry, I have not pursued this any further. But now I'm quite amused to see that the interest in such things actually is increasing, and over the years, eminent experts have contributed to this field and enriched this field. I must also congratulate the Department of Physics for being the standard role model for having organized academic activities intensely during this critical time, which is also part of their Silver Jubilee celebration. I am sure that the eminent experts who have been actually requested to share their expertise and knowledge with our students and other scholars and faculties at Assam University platform. I not only welcome you, but also I am deeply indebted to all the speakers who have agreed to talk on these very significant theme in not only physics or chemistry, but that concerns the whole concept of the cosmic world. So with this few words, I congratulate the department, and I wish this international webinar great success, and I wish that this generate a lot of enthusiasm and inspire our students to take up research in this direction as well. And once more, I welcome all the esteemed speakers in this international webinar. Thank you so much.
Thank you, sir. I would like to request Professor Raychaudhuri to speak a few words, just as a starting point.
Well, you will hear me in detail in a few minutes, but I would like to start by congratulating Assam University for your Silver Jubilee. And I'd also like to thank you, Atri, personally, and also the department and the School of Science for organizing this program. The one advantage of the pandemic and the lockdown, and most of the things are bad, as we all know. But one advantage has been that it has familiarized people with more of these webinars and this format. And it allows you to organize things with much less effort and much less amount of resources involved. So I think, it is good, and I'm happy to see there are so many young people who want to listen to these things. And perhaps this is setting a future trend, and you will have more of these in the future. So I wish all success to you. I hope this thing goes off well, and of course, all the speakers, apart other speakers, are all eminent speakers. They are, Atri and I have had long discussions to choose them, and I know that they are all experts in their field, and they're also very good presenters. So I hope you will enjoy this. And to the younger people, please sit back, relax, and enjoy the stories you will hear. And if it inspires you, of course, you will have to put in work and learn things more. But for the moment, let us just have the event, and I hope it goes off very successfully. Thank you. Yeah, I'm done.
Sorry. Thank you, Professor Raychaudhuri. Now, I would like to request Professor Indrajit Sharma, the head of the Department of Physics, Assam University, Silchar, to speak a few words in this occasion. Professor Sharma, please.
Thank you, Professor Atri. At the outset, I congratulate the convener of the seminar, Professor Atri Desamukhia, and the entire team of the Physics Department for organizing these 2 days seminars. We, Department of Physics, welcome the speakers, Professor Raychaudhuri, TIFR, Mumbai, Professor Rajesh, Gopal Kumar, TIF Bangalore, Professor Paskule, Sarpico, CNRS, Dr. Rishi Khatri, TIFR, Professor Navakumar Mandal, SINP, Kolkata. Sir, Madam, we are very fortunate to get your valuable time and for giving the opportunity to listen your lectures on standard model and beyond. The participants in the seminar will get benefit to understand the basic concepts on the standard model and further will be exposed to the frontier research in this area. I pray the seminar a grand success. Thank you. Over to Professor Atri. Thank you. Professor Atri, over to you.
Thank you, Professor Indrajit, for your kind words. With this, this was just a formal inaugural, and I take this opportunity to actually thank all the speakers who have agreed to speak in this occasion. It's really difficult nowadays to manage time because lots of seminars and these things are getting organized online, and everybody is looking forward to listen to them. But in spite of that, they have spared their valuable time to be here with us and sharing with us the forefront activities and the basic issues in this field. And I would also like to thank the participants for showing their interest in joining the event, because without them, there is no point organizing an event. It is for them only we are organizing the event. And I would like to thank all my colleagues in the department for helping me out, and also the research scholars of the department, research students, who have helped a lot whenever any like assistance was required. And I hope these 2 days will be a great academic discussion session. With this, I would like to stop here. It's 4 o'clock already, and we should start our technical session. Without any break, we just proceed to the first technical session with our first, what should I say, with our first talk of the day, which will be delivered by Professor Raychaudhuri. As you all have already got the information from the schedule that I have already sent to you earlier. So Professor Raychaudhuri is going to speak on developing the standard model. And the abstract of the talk is, just to read through the abstract, the standard model of strong and electroweak interactions is the reigning theory of the interactions of elementary particles. This talk will trace the development of this standard model, starting from the discovery of the electron in 1897 to the discovery of the Higgs boson in 2012. The physics will be explained in simple, non-technical terms. Reasons for expecting more physics beyond the standard model will also be touched upon. So this is his plan of the first lecture. And let me introduce Professor Raychaudhuri before the audience. So he is a theoretical physicist from Tata Institute of Fundamental Research, Mumbai. He works in the field of physics of elementary particles and their interactions. He has got his PhD from the University of Calcutta and worked as a postdoc at TIFR as well as CERN. He was a faculty in IIT Kanpur for quite a long period of 9 years, and then he joined as a faculty in TIFR. So his research interests are mainly interfacing theory with experiments, especially the physics of electroweak interactions. And otherwise also Professor Raychaudhuri is a well-known name in the science popularization and the history of science. So we wish that this talk will mesmerize the audience. This is my personal wish. And I request Professor Raychaudhuri to please start his deliberation. Thank you.
Thank you, Otri. Let me first share my screen. I'll share my entire screen. Is it okay? Screen is visible? Is the screen visible?
Yes, sir.
Yes. Okay.
Sorry,
So let me.
Yeah, I was in
Yes.
mute mode, so it is visible. Yeah.
Yes. All right. So let me thank Otre for that warm introduction. And I think she has raised your expectations to everyone. She's probably raised your expectations more than I can fulfill, but I will try my best. So as she has told you, the topic which I will, oops, what's happening? The topic which I will be talking about is developing the standard model. And I will be talking about how the standard model arose, what are its ingredients, what are the ideas behind it. As Akshay has already told you, I will be keeping it reasonably non-technical, no mathematics as far as possible, only very simple mathematics which everyone can understand. And I'll try to give you the basic ideas, the physical ideas behind it. Towards the end of my talk, I will also tell you why we would like to develop beyond the standard model, and that will set the stage, I hope, for the other talks which you will hear. So without ado, let me start. So let me introduce you to the fundamental particles. The standard model is the theory of the fundamental particles and their interactions. So the fundamental particles, as we know them, consists of a bunch of particles which are called the fermions, which means they have spin half and obey Fermi-Dirac statistics. So there is a bunch of three neutrinos, the electron, the muon, and the tau neutrino. Yes.
Are you showing the screen? Actually, we are seeing you, not the screen.
Oh, that shouldn't be happening. I have shared this. Oh, this share screen is gone, is it?
Possibly.
I see. Okay. Let me try again. I'm sorry.
That's all right. I could see Professor Sudhakar joining. He is there listening to your
All right.
class.
That's nice. Yes. Yes. I saw a glimpse of him also. Is my screen visible now?
Yeah. Yeah. But you have to take it to full screen mode. Otherwise, it's okay.
Yes. Is it now in full screen mode?
Yes, perfectly.
All right. So this was visible. Anyway, so I think I've already talked about it. This is my talk, developing the standard model.
No,
So I will. Yes.
It is one-sided. It's one-sided. I see only half the screen. Left side is not.
Just wait a little bit.
Sir,
Just
you
wait a
may do it, sir.
It is perfect.
Do you see how?
No. Earlier mode was all right. This is the problem at Professor Panda's end. It's perfectly all right. Now.
Okay, let me check.
I think it's a little slow.
Yeah.
It's a little slow. It will come. I think it will come as the full screen.
Yeah.
Is the full screen visible to most people now?
I think so.
All right.
Sir.
Okay.
Yes,
So
sir,
let
it's
me go
okay
ahead. Yeah. Thank you. So now then there are these three particles which are called the leptons, charged leptons, the electron, the muon, and the tau. I'll talk more about them as we go. And then there are this bunch of 6 quarks, which go by the fancy names of up, down, charm, strange, top, and bottom. In addition to that, there is a bunch of particles which mediate the interactions. I'll talk more about that. The W plus and W minus, the Z naught, and the photon, most familiar one. And there's a bunch of 8 gluons. So that's one set. And there's one particle which was recently discovered, and that is the Higgs boson. So this complete set of particles, these are the building blocks of the universe. This is what everything is made of. And this is what we will be talking about in the rest of this talk. So let's begin at the beginning. and with the earliest discoveries. So what are the earliest discoveries? Actually, what is interesting is the earliest discovery was of one of these particles. And that was the discovery made by Sir J.J. Thomson in 1897. We all know that he discovered the electron. And here you see a little picture of the apparatus which he actually used. This is preserved in the Cambridge Museum, Cavendish Museum, which he actually used to find this electron. Then in 1911, Rutherford, also at the Cavendish laboratory, discovered the proton using this instrument, the famous gold foil experiment. And you see here, this is the very neutral scattering. But he was able to discover the hydrogen nucleus of the proton. This was completed by Chadwick in 1932, and with this apparatus, he used this apparatus to discover the neutron. So with the electron, proton, and neutron, we have our modern idea of the atom. What is that idea? That there is a nucleus which has, so I will consistently use the orange color to indicate a positive charge, the blue color to indicate a negative charge, and this off-white color to indicate a neutral. So these are the protons, these are the neutrons, and then there are the electrons which are spread in orbitals around them. So this picture, we owe it to Rutherford to have the nucleus and Chadwick to have the neutrons in it. And the idea of the electrons in the orbits and how they are arranged and how that happens, the orbitals, we owe to these four gentlemen. Niels Bohr, who first discovered that the electrons have these discrete levels. Schrödinger, who gave us the equation by which we can calculate them. Max Born, who told us what the meaning of the wave function is and what these orbitals physically mean. And Dirac, who told us how to calculate the electron spin and gave us the relativistic version of Schrödinger's equation. So that's the modern atom, which you are probably learning in your MSc classes anyway. Well, after the discovery of the neutron, this question was asked by Heisenberg. You of course know Heisenberg for the uncertainty principle, but here is a question which he asked in 1932. And the protons are all positive, so they must be repelling each other. We know that like charges repel. And the neutrons are neutral, so they neither attract nor repel. So why doesn't the nucleus just fly apart? Why don't these neighboring protons just push each other away? So how come the nucleus is sticking together? So that's the operative one. What sticks it together? So he said there must be a force of attraction between the nucleons, that's the protons and neutrons. And it must work between the neutrons also, otherwise the neutrons would simply drift away. So this force was known, became known as initially as the strong nuclear interaction, but nowadays we just call it the strong interaction. Now why do we call it strong? Let's see how strong this force is. So this is the force between the electron and the proton in a hydrogen atom. So E squared by 4 pi epsilon naught, and A naught is the radius, Bohr radius of the atom. And we all know that the potential strength of the potential is 13.6 electron volts. Now, if there are two protons inside a nucleus, the charge is still the same, but the distance, instead of being the Bohr radius, it will now be the nuclear radius. Okay, at least something like the size of the nucleus. That's why I put approximate thing here. But now we could rewrite this as by just multiplying and dividing by A naught by Rn. So what is A naught? This part, this is exactly what we have here. So it is 13.6. Now A naught is about 10 to the minus 10 meters, 1 angstrom, half an angstrom actually. And the radius of the nucleus is about 10 to the minus 15 meters, a femtometer or a Fermi. So this factor here is like 10 to the 5. So that's 13.6 into 1 lakh. And that's about 1.36 mega electron volts, a million electron volts. So roughly this interaction is a lakh of times stronger. And to have an idea of what that is, imagine the weight of a small mouse and the weight of a big SUV. So the comparison between those gives you the comparison of strengths between these two forces. So clearly the nuclear force is very strong indeed, and that's why obviously you call it the strong interaction. Now, there is an issue of force mediators, and we already learned that from electromagnetic theory. So in the quantum version of the electromagnetic theory, The electromagnetic force is due to the exchange of virtual photons between charged particles, for example, protons, and these photons are just the quanta of the electromagnetic field. This theory is called quantum electrodynamics. So I'll give you a cartoon to explain what it means. Imagine these two stick figures which are on an ice skating rink, so no friction at the bottom. So they come close and one guy throws a ball at the other. Now what happens, by throwing the ball, this guy recoils back. The guy who catches the ball also moves back. But suppose you couldn't see the ball. Suppose the ball was invisible. What would you say? You would say that these two guys repelled each other. So similarly, when you have two protons and they exchange a photon, basically they repel each other. What we see is only the repulsion. We don't see that virtual photon. So this is the idea of that forces are mediated by particles. Well, basing himself on Heisenberg's idea of a strong interaction, Yukawa in 1935, he tried to create a theory of this interaction. What he said is that just like electromagnetic interaction is due to the exchange of the spin 1 particles called photons, the strong interaction must be due to the exchange of spinless particles with mass around 200 times the electron mass. I'll explain this one. So he called them mesotrons because they were sort of middle. Meso means middle, middle in mass between the electron and the proton. And later they were called mesons. Specifically, these particles became known as pi mesons, and today we just call them pions. So the name has sort of shrunk over the years. And what Yukawa had said is that just as collisions between charged particles leads to the emission of photons, collisions between nucleons at high energies can lead to emission of pions. And then the idea to look for them in cosmic rays, the first people to do that were actually in India. D.M. Bose and his student Raychaudhuri were the first people to start looking for pions in cosmic rays. Unfortunately, their equipment available to them in India was a little primitive, and so they were not actually able to find them. But certainly they were the pioneers in looking for it, so I just wanted to inform you. This is one case where this was done in the 1940s, early 1940s. So a little word about cosmic rays. So typically what happens with cosmic rays, which were discovered by Victor Hess in 1912. By the way, whenever you see a golden circle around that, that means the person received the Nobel Prize. People, poor fellows who don't have that golden circle. Okay, anyway, so the cosmic rays typically are showers of particles which are coming from the cosmos. And initially people didn't understand them. You detect them somewhere down on the ground like this. But the explanation that basically one particle comes and it hits some nucleus, and then the high energy of that particle gets converted into a shower of new particles. Some of those new particles also have their own masses, energy, so they get converted into others. So you have a whole laboratory of new particles. And here you can see the pi minus, the pi plus, and so on. So these pi's are the pions which are created there. This whole idea of showers was invented or was worked out by Homi Bhabha and Walter Heitler in 1936. So another major Indian contribution at an early stage. Now, when people began to look for these mesons, so the first thing which we found was a different kind of meson called the mu mesons, or today we call them muons. So they were discovered by Anderson and Niedermeyer in 1937. And you see here a track in a cloud chamber left by a muon. So it's just moving straight through. It's a charged particle creating a track. However, the mu meson is not Yukawa's meson. Yukawa's meson came only in 1947. It was discovered by Powell and Occhialini and their team. And Powell got the Nobel Prize for it, of course. And these are the actually first tracks they saw. Now these tracks are interesting. Only this little part is the pion. The pion comes here, decays into a muon and an invisible neutrino. This is the muon track, and then the muon decays into an electron and neutrinos. So each of them are like that. So this little part is the pion track. And this also explains to you why D.M. Bose and Raychaudhuri were not able to see it, because their resolution was not small enough to see such small tracks. They could only see the bigger tracks. Anyway, this one is clearly Yukawa's meson. It satisfies all the properties. So if this is Yukawa's meson, then where did this muon come from? So that is a question which was asked by Isidore Rabi, who also won the Nobel Prize for something else. He said, who ordered that? Where did that come from? We didn't ask for it. but it's there all the same. And that is a question which we are still asking. I'll come back to it again. The next question is, what prevents a proton from decaying into two pions? Because the mass of the proton is about nearly 938 MeV. The pions are like 140, 135 GeV. So why doesn't the proton simply break up and decay into two pions? It should happen, but it doesn't happen. So you say, okay, I've written down the masses here. So there's lots of energy, lots of mass. You can easily decay into these. Should be happening, right? But it doesn't. Okay, if protons decayed, we would all decay, right? They are mostly made up of protons. And then the answer was found by Stuckelberg in 1939. He pointed out that it must be that the proton, and then he later showed that every baryon carries a conserved quantum number B equals 1, which is called baryon number. And this is conserved in all the processes. So since pions and the mesons have B equal to 0, the above decay is forbidden. The initial state has B equals 1, final state has B equals 0. So that can't happen because it's conserved. So the result is all other baryons, in fact, they are all seen to decay. One baryon is always seen to decay into something which includes one more baryon. So that B is always there. And the proton is the lightest of the baryons. So there's no other baryon it can decay into, so it remains stable. That's the discovery of baryon number. And then we come to the Fabulous 50s. Okay, so this is the timeline of the discovery of the new elementary particles. So I've started with the electron here, and you see the discovery of the Higgs here in 2012. But during the 1950s, a whole bunch of new particles were found. So you found many things: pions, kaons, lambda, sigma, cascade, and so on, phi, omega. Lots of new particles were discovered. Basically, a period a little before 1950, intensely through the 1950s and towards the early 1960s also, mostly by studying cosmic rays. So this is, I call it the period, the Fabulous 50s, because so many particles were discovered. Actually, so many were discovered that this thing is now called the particle zoo. So what happens if you go to a zoo? In a zoo, there are here there are two kinds of particles, leptons and hadrons. The analogy is like this. If you go to a zoo, you will see places where the smaller things are kept. Okay, there are bird cages where you will see the birds. Then there were cages where small animals like rabbits are kept. Then you will find other areas where you put more heavier, bigger animals like deer. And of course, there are some of the really big and heavy animals like the hippo and elephants and rhinoceros and so on. So the particle zoo, and of course, these are all different, each has its own properties, own behavior, exotics. So all of them together form a zoo. And particles also, of course, how can I forget that? You go to a zoo, there'll be lots of flowers and plants, and there'll be butterflies also around it, so very light ones also. Now, the equivalent of the leptons of the birds are the 3 neutrinos, which are very light particles. And then there are the leptons, which I said, the charged leptons, the electron, muon, and tau, and those are the leptons. So these are the leptons, which I showed you in the very first slide. Then there are the hadrons, which are of two kinds. There are the mesons. I've already introduced to the pion, the pi, also the k, rho, and so on. And these are the middle heavy particles. And then there are the very heavy guys, the hadrons, which includes the proton, neutron, and then there are many others, delta, sigma, cascade, omega minus, and so on. What about the butterfly, the light one? Of course, that's the photon, which is no mass at all. Actually, it's completely massless. Okay. By the early 1960s, there seemed to be at least 30 to 35 elementary particles. And the number has kept on increasing. Today, the Particle Data Book, which is a standard book brought out by the Particle Data Group, which is an international group, they list more than 300 particles. So, if there are so many elementary particles, that's a very unsatisfactory state of things. So, in fact, this was so frustrating that Fermi answered a student once with this statement. He said, "Young man, if I could remember the names of all these particles, I would have been a botanist." Botanists have to remember the names, Latin names of many, many plants. So he didn't like it. He felt that physicists should be able to find some system. Actually, that system was found, and that's what I'm going to tell you about now. So, the system is called the Eightfold Way, and I'll explain to you why. So, the idea is that all these quantum number particles carry certain quantum numbers, conserved quantum numbers, and one of them is called isospin. So, isospin is like spin, so this is the third or the Z component of isospin. And there's another one called hypercharge. So these are all found by seeing what decays are allowed and what are not allowed, selection rules basically. Now what you find is that if you take the particles and you can identify that each particle has this quantum number. So if you plot them along this plane, then what you will find, so take a bunch of particles which are known as the pseudoscalar mesons. Pseudoscalar comes from the Lorentz property. It's not too important to worry about it, but let's see, they all belong to the same class. And what you find, the pions belong to them. So the pi plus and pi minus, of course, they have opposite quantum numbers. So they are y equal to 0 and t3 plus half and minus half, and then you have the pi naught in the center. The k plus and k minus will come in these points. And the k0 and its antiparticle, the k0 bar, will come at these points. And then after some time, so there are how many of them? There are 7 of these. And then there's another particle eta naught, which also comes in the same place. So it's like these guys have shifted. They're both competing for that central place. So you can just draw a hexagon like this. And then there are 8 particles which belong to this particular structure. Okay, fine. So this was introduced by 2 different people independently, Murray Gell-Mann and Yuval Ne'eman. And Gell-Mann, who died recently, actually, I think only earlier this year, and he was a very knowledgeable person, and he knows a lot about various religions and scriptures, including Buddhist scripture. So as you know, the Buddha had preached the Eightfold Way, Eightfold Path to salvation. And so because he had 8 particles here, he said this is the Eightfold Way to understanding the universe. So in analogy of the Buddha's Eightfold Way, he called it the Eightfold Way. So that's a fanciful name. It's not to be taken any seriously, because what it really means is that if we look at the mathematics, there is a group SU3 to which all these belong, and this is the 8 octet representation of SU3. So nothing to do with the Buddha, it's only an analogy. Now if we replace these pseudoscalar mesons by another class of vector mesons called the vector mesons, another class of mesons called the vector mesons, and then you'll find that the same pattern repeats. There are 3 rows. There's a k star plus and a k star minus. There's a k star 0, a k star 0. And in fact, there is an omega naught, which comes in place of the eta. So once again, we have the same structure repeating. And then what Gell-Mann and this works even for the baryons. So if you look at the you look at the mesons, but if you look at the baryons, once again, you could put the proton and neutron here, the 3 sigma particles here, and the 3 cascade particles here. And just like the previous one, there's a lambda naught which competes with the sigma naught for this central place. So once again, draw the same hexagon. Now this can't be a coincidence, can it? That the same pattern is repeating again and again. Then that same pattern must indicate that there is something going on, something close going on. So let me now take you on a flashback. Flashback to the periodic table. You remember that in the middle of the 19th century, there were so many elements, and they we were learning, this is actually the number of elements known in 1869, and they all had some specific properties. So it was Mendeleev who showed that if you just take the elements with similar properties one below the other, then you can put them in a table, and elements which come one below the other are all having the same properties. So then there is some systematics to this. The properties of elements are repeated. And he was able to go ahead and say that, okay, there are these 3 empty spaces here. So he said that there will be 3 new elements, and he was able to predict their properties. And lo and behold, soon people discovered scandium in this place, then gallium here, and germanium here, they were discovered. And in fact, all these other empty places gradually got filled up. So this is something we all know. Then we got to 1922, in which Niels Bohr showed that the properties of the elements actually show repetition because they have the same outer atomic structure. It is because they have structure, the same structure is repeating. That's why you are seeing the same properties. So here is, for example, you look at the alkaline earths, the lithium, sodium, and potassium. They have some internal structure, but the important thing is that there is this outer atom. Okay, this is how you write them using the Aufbau principle. So this outer electron, 2s1, outer electron, 3s1, outer electron, 4s1. That's why the properties are repeated. So we all know this. I mean, you've studied this, I think, even in high school. So let's come back now to the Eightfold Way. So Gell-Mann pointed out that not only are there octets of SU3, but if you use the SU3 group, you can also have decuplets. So there should be particles which you can arrange as a set of 10 particles. And in fact, he was able to find some of them. So the deltas come in a row like this. The sigma star, excited sigmas come in a star like this. The excited xis come in like this. So that's how, what is it? 4 and 3, 7 and 2, 9. So there's one missing. And in fact, if you draw this triangle, it's only to be expected it will complete here. So there's one place missing here. And this particle, he was able to look at the properties of these particles and predict the particles. This is exactly a repetition of what Mendeleev had done. There seemed to be an empty place in this decuplet, and he was interpreting that you should find a particle like this. So this was predicted in 1957. And then in 1964, people discovered a new particle called the omega minus, whose properties fitted this perfectly. So this became complete. And of course, once you have predicted and something has been shown that it works, then just like people started believing the periodic table after the discovery of those 3 elements, everyone started taking the Eightfold Way seriously. Well, not the name, but the idea. Well, Gell-Mann then followed Bohr. Both Gell-Mann and Zweig, they took this further. And one more convention I've used is that I'm showing you color photographs of people who are still alive, black and white for people who have passed on. So I won't mention that explicitly. You can just tell from the color. So they went just as with atoms, the repetition of properties of the hadrons is because they are composites of 3 smaller particles. So Gell-Mann called them quarks, Zweig called them aces, but the name given by Gell-Mann has stuck. So there were 3. There was the up quark, which is positively charged, the down quark, which is negatively charged, and another negatively charged and heavier particle called the strange quark. I'll tell you why this strange name has come. Okay, but the idea was that when you look at these particles, then typically the pion is a bound state of an U and a D bar, and each particle quark has its anti-quark. So a U and a D anti-D. The kaon is a combination of a D and an anti-S. The proton is a combination of 2 U's and a D. So these are the heavier ones, the baryons. These are lighter because there are only 2 of them. There are 3 here. And the neutron is the mirror image of this. It has 2 D's and a U. And similarly, you can find it for all of them. In fact, here is the baryon octet, and you can find the quark structure of all of them. UUD, UDD, I just showed you these. US, UDS, DDS, and so on. So these are the same structure, but in different combinations. Now, of course, if you have quarks, like the electrons in an atom, you can pull them out of the atom and you can check the properties. But the problem with quarks is that we can't pull them out of because the interaction is so strong. Let me explain to you. Let's take a rho, for example, a rho particle. Rho is a UD bar state. So it's a UD bar state in a spin 1 state. Now, normally the interaction, the UD bar will be at the bottom of this. So the potential between quarks actually grows with distance. It's like a harmonic oscillator potential. As you grow further, it will grow with distance. And when it grows with distance, what happens is, suppose I try to pull these apart, yes, which means I'm giving more and more energy to the system. So if I pull this apart, at some stage, it becomes more energetically favorable to create a quark-anti-quark pair out of the vacuum. So rather than push this further up the potential, it's easier to just create a quark-anti-quark pair out of the vacuum. The extra energy I put in goes into creating the mass of this quark-anti-quark pair. And after that, these things just bind with the original ones. and everything is a zero potential again. So instead of being able to pull out the quarks, what you've done is you made the original rho decay into two other particles, which are a pi naught and a pi plus. So giving energy to the rho instead of separating out the quarks, it just makes the rho decay into two new pions. So whenever you try to separate out quarks, what you will just get new things coming out. So it's a bit like, if you try to cut a bar magnet, if you try to cut it into two and separate the poles, new poles will come up at the cut edges and you will again have two bar magnets. So it's a little bit like that. That's an analogy, of course, but this is the idea. The reason is that the interaction is so strong that rather than pull it out of the potential, and the potential also grows. So therefore it's a confining potential. You cannot really pull it out. So quarks cannot be isolated, as I said, they are confined. Now, of course, what are the interactions which cause quarks to be confined? These are, again, there'll have to be some exchange. And this interaction is now mediated by this bunch of particles called gluons. And there are three kinds of colors, which are like the charge, analog of charge. I'll come back to this again. And gluons correspond to an octet of SU3, then there are 8 gluons. So this is not the same SU3 as of the mesons. This is another SU3. And basically it's an artist's picture of the inside of a proton. So here's the two up quarks, here is the down quark, and then there's a bunch of virtual quarks which are gluons and virtual quarks popping in and out of the vacuum. So all virtual, so there's sort of, it's like something bubbling inside. That's the picture we have of a baryon. So, and then of course, if this is the real strong interaction, then of course, if you have another nucleon, then the interaction between those two nucleons is like a van der Waals force between atoms. Atoms are neutral as a whole. But if you put two atoms next to each other, there will be some dipole or a quadrupole or higher order interaction, which are known as van der Waals forces. They cause the cohesion property of materials. So this strong interaction between nucleons, which was modeled with the pion by Yukawa, this is really actually like a van der Waals interaction between bunches of quarks. So that's the picture we have of the. Now, one more thing that I talked to you about the strange quark. That is because there seem to be certain strange selection rules for heavy particle decays. For example, the xi naught or the cascade particle decays to a lambda naught and a pi naught, but it doesn't decay to a neutron and a pi naught. Okay. But if you write down the masses, this mass is 1315 MeV. So it decays to 1116, but then it should also decay to 939, which is less than 1116. But that doesn't seem to happen. So once again, the idea of Stuckelberg was repeated by Gell-Mann and Pais, and Gell-Mann will keep coming, unfortunately, or fortunately, he's such a brilliant man, he contributed many things. Gell-Mann and Pais in 1955, and also Nishijima from Japan independently, said, okay, there must be one more conserved number. And that's not there in the neutron, but is there in the lambda naught. So when this goes, the number is conserved. When this happens, it's not conserved. And because this gave it the strange selection rule, he called it strangeness. And Gell-Mann fitted it into his quark model by just saying strange quark carries a strangeness of +1. The other two quarks carry strangeness of 0. So that was the idea. So this was these quantum numbers called like baryon number strangeness, which come, they're just postulated to explain the behavior. These are called Flavour quantum numbers. Once again, fanciful name. In fact, in 1970, these three gentlemen, all alive, Glashow also won the Nobel Prize, Glashow, Iliopoulos, and Mayani, they showed that the strange quark also has a partner. And that again carries a quantum number of its own called charm, with strangeness, charm, fanciful names. And it's called the charmed quark, and it would have charm of 1. Now, of course, this was a theoretical prediction. So you could take a CC bar bound state is like positronium. And what is positronium? Positronium is an electron and a positron bound together, a particle, antiparticle. So you see here, these are actually, if you look carefully, these are actually both going in circular orbits or elliptic orbits around a common center of mass. If you keep watching one of them, you will see it's going around. Though they look like they're going randomly, they are not. So this kind of bound state is called charmonium. like positronium, it's called charmonium. And in fact, in 1974, one team led by Bertrand Richter discovered a new meson, and they called it the psi. And Sam Ting and his group also discovered the same meson, and they called it the J. And then for some time, people thought two different mesons had been discovered. But after some time, people realized that it's the same meson. So today it has a hyphenated name. It's called J psi. It's called the J psi, and it's basically the charm bulb state. So of course, charm was also discovered. So at this point, people knew that there was an electron neutrino and an electron. There was a muon and a muon neutrino. There were the up and down and the charm and stray. So these all seem to come together, and you could call it the first generation. The muon and charm and so on were called the second generation. So that's all people knew at that time. And then in 1973, Kobayashi and Masukawa, they studied a slightly obscure phenomenon called CP violation, which had been discovered in 1964. And they said that yes, this can be understood if you replace the two generations and put a third generation. Third generation, but what is there in it? Nobody knows. So if there's another generation with similar particles, then yes, you can understand this phenomenon of CP violation. Okay, big deal. Wasn't taken too seriously at the time, but afterwards, in 1975, Martin Pearl discovered that there's an analog of the electron and muon called the tau. In 1977 came the discovery of the B quark, which also carries a quantum number called beauty. And then came the top quark in 1994, analog of this, and this was completed in 2001 with the discovery of the tau neutrino. So the third generation does exist, and it was predicted by these people from something which was almost unbelievable at the time. Not surprisingly, both of them got the Nobel Prize for this deep insight. The question still remains, why do we have three generations? I mean, nothing in the standard model which we know would not have worked if we had only one generation or two. Or why not four? Why not five? So that question asked by Rabi, who ordered that, is still valid. We don't know the answer to this. Not only that, there is the issue of fermion masses. Okay. So what happens there? So here is a plot where I have taken the various, this is the first generation, second generation, and third generation. I plotted all the masses one after the other on a scale of giga electron volts, GeV. GeV by C squared, of course, but put C to 1. But you see here that they are spread all over the place, from the top quark, which actually is at 175 GeV, to the neutrinos, which are at a few electron volts. Okay, so sorry, this should have been these are minus. Okay, this has got repeated. This is 6, 8, and 10. So the variation is actually over 7 orders of magnitude. Excuse this goof up here. The top quark 172 GeV, the neutrino is less than 1.8 GeV. So huge variation. Okay. And then also you see that in general the masses have become heavier. This is a log plot, remember. So this is actually quite a lot heavier when you go from the first to the second generation, from the second to the third generation. Clearly the quarks are always seem to be heavier than the leptons. Okay. Except here the B is a little light. And then there's a pattern. You see, there seems to be some pattern. Clearly as you go from the neutrino, the mass increases. It increases, but then it turns around here. And turns out even more dramatically here. And there's some increase this way. So there is a pattern. It's clear that there is a pattern, but nobody understands this pattern. Nobody knows why this pattern is. And there are, of course, models and theories, but the answer is not known. So this is the point at which I could call a small gap. And this is, I've told you about all the basic particles and how they behave. So let's keep the intermission short and resume. And now we'll talk about how the particles interact with each other. So for the particle interactions, of course, the oldest interaction known among them, anything which has mass, has this interaction of gravity. We know that gravity, the first understanding came from Galileo, with the laws of falling bodies, Newton's law of gravitation, and finally Einstein's theory of general relativity. Of course, no Nobel Prize for these people. They were born long before Nobel Prize came. Then electromagnetism is the other great interaction we know of. The properties of electricity were discovered by Gilbert. The connection between electricity and magnetism came from the experiments of Faraday. And finally, the unified theory was given by Maxwell. So these are all known to us. Then we have the strong interactions, which I've just told you about. The nucleon-nuclear interactions were postulated by Heisenberg. Yukawa gave the Meson theory, and Gell-Mann created the actual quantum chromodynamics, which I will talk about in a few minutes. Then in addition, there is the weak interaction, which causes a bunch of interactions, including beta decay. And the beta decay was discovered by Rutherford in 1899. Fermi gave the first theory of weak interactions, and Schwinger explained that they are due to the exchange of a different kind of boson called W boson, which I will talk about in a moment. So these four are the basic particle interactions we know about. And these have a deep connection with symmetries. So what do you see here? You see a sort of what is a two-dimensional representation of a sphere. And I've drawn a line in the middle to show you its diameter. So I've now set this sphere rotating. Can you see that it's rotating? Well, I can't. I wonder if you can. The reason you can't see it is because whatever configuration it takes when rotating looks exactly the same. There's no difference at all. But suppose this is a rubber, like a rubber ball, okay? It's a rubber sphere, and I sort of stretch it out on one side. Suppose I stretch it out. Now you can see that it's rotating. But if it's a rubber sphere, then after some time it will come back to what it was. It will come back to the original spherical shape and you won't see it rotating. Let me repeat this. So as you distort it, you can now see the rotation clearly, which means that it's no longer the same when you rotate it. That's why you're being able to make the difference. But after some time, it comes back to that. So the rotation is invisible when the rubber ball is symmetric under rotation. But when you got the restoration of symmetry, then you got the symmetry back again. And the restoration of symmetry was due to the elastic force. So you could say either of two things. You could use a mathematical language and say the symmetry is restored, or the symmetry is the fundamental thing, behavior of this. Or you could say there is an elastic force. So symmetries and forces are just two different ways of talking about the same thing. Who taught us to think like this? Not unexpectedly, Albert Einstein. And he first applied it to the theory of gravitation. So what does it say? It says there's a symmetry between all frames of reference. Okay, that is, the laws of physics appear the same in all frames of reference. You can't tell between one and the other, including those with relative acceleration. All that you will see there is you will see the force of gravity. So the action of gravity, gravitational force, is to restore this symmetry between frames, to make all the laws of physics same in all frames. And in fact, he also showed that just like the rubber ball, the space-time around us behaves like an elastic membrane. The masses tend to deform it and give rise to a gravitational force, which then tries to make it flat again. Just like the rubber ball elastic force tried to make the rubber ball spherical again, same kind of idea. So if you have flat space-time, I've just drawn this grid drawn on it. Then if you put a particle in the middle, heavy ball like the Earth, then the space-time gets distorted, and that distortion will make things move along that distortion. So in curved paths, which is the result, which we call a gravitational attraction. And the most dramatic proof of this was discovered recently when the LIGO collaboration discovered that you can, of course, if you suppose I move this ball up and down, okay, then there will be waves, okay, this will start vibrating. So actually when two black holes collide, you get this vibration in space-time, and those faint vibrations, which are called gravitational waves, have been detected. So this idea is clear. I think you will hear more about it in Rajesh's talk. Well, symmetry can be applied to electromagnetism also. And for that, you need to look at quantum mechanics. In quantum mechanics, of course, the wave function is a complex number, but only the modulus of that quantum is physically measurable. And Max Born taught us that it physically corresponds to the probability density. So if you think of plotting the real and imaginary part in the complex plane, then any rotation you make like this angle theta, this angle which it makes, is not measurable. What is measurable is the length of this. That's the modulus. So there is something which we cannot measure. So then if we change this angle, as this angle changes, nothing changes. So that's a symmetry. So all physical configurations should remain symmetric under a change of phase of the wave function. So this, and again, this, what causes that symmetry to remain unchanged? There must be a force which does that, just like the gravitational force or the elastic force. The restoration of symmetry is due to the electromagnetic force. So the change of phase is sometimes also called a change of gauge. Okay, that's just a different thing. And these three gentlemen who invented this, Hermann Weyl, Fritz London, and Vladimir Fock, they called it the gauge theory of electromagnetism. So the word gauge theory has stuck. And actually it's become more general. So now gauge and phase are not the same except for electromagnetic theory. So having invented this, so now it's a little bit of mind-boggling to think that all the electromagnetic, yes. So all the electromagnetic, can I be heard?
Sorry to interrupt you, but can I ask one thing, if you don't mind, please?
Yes, go ahead.
Ma'am, will you provide the recording for this? Sorry to interrupt you, ma'am, but please, sorry.
Sorry, Harshita,
Sorry?
this is not a platform to put these questions. You can write your questions in the chat box. Please don't disturb the speaker. Harshita.
Okay, sorry, I'm really sorry.
Okay. Yes, so let me go on. I'll answer all your questions at the end. Okay, so so now we are called what we call gauge theories, and it's a little mind-boggling to think that just the fact that we cannot measure all the electrical phenomena we see around us, including the ones which I'm using to deliver this talk to you, and of course much more spectacular things, for example, like lightning and so on. These are the ones all originate because we can't measure the phase of a wave function. But that's how it is. Well, let's now pass on to weak interactions. So processes like beta decay, that's what was discovered by Rutherford, they require the exchange of a charged boson. So the way we understand it is like this. Say you have a neutron which is undergoing beta decay. So it changes into a proton and emits something called a virtual W boson, which then decays into an electron and a neutrino, anti-neutrino to be precise. So that W boson in the middle was the exchange particle. But since the proton decays, neutron decayed to a proton, that W had to have a charge. It was a W minus. So if there is a W minus, there will be its antiparticle, which is a W plus, which already tells you that there must be two gauge bosons. So if there are two gauge bosons, there must be at least two charges and perhaps more. So Schwinger actually came up with this idea in 1956, and he gave it to his student Glashow as his PhD problem to find a correct model which will incorporate this gauge theory of the weak interactions. What Glashow discovered was that the only valid way to do it, and he won the Nobel Prize for this work, is that the only valid way to write down this gauge interaction is to combine it with electromagnetic theory and have four gauge bosons. So we get a unified theory, which is called the electro-weak theory, electromagnetism plus weak. So you have the W plus and W minus. You also have a neutral particle, which is now called the Z naught. And of course, there is the photon. So these three give you the weak interactions. This gives you electromagnetism. So the gauge theory of electro-weak interactions gives you the one unified theory. So now we don't have these four forces anymore. We have three forces: gravity, electroweak force, and the strong force, which I'll come to. So there's a question that then why do the electromagnetism and weak interactions seem separate? I'll come to that in a moment. So now there is a question about the masses of the gauge bosons. Any gauge symmetry, if you look at it, it demands that the gauge bosons be massless. Okay. And that means the rest mass must be zero. This was discovered by Pauli in 1942 and then rediscovered by C. A. Lang in 1953. So now if the gauge bosons are massless, the force is long range. That is, it goes as 1 by r, which is like gravitation and electromagnetism. We know that they go as 1 by r. But if the gauge bosons are massive, then the force is short range. This is like a Yukawa potential. So there's an exponential factor here, which dies down much faster than 1 by r. And lambda is some typical scale, and you can show that lambda is proportional to 1 by the mass of the exchange particle of the gauge boson. So if the mass is large, lambda is very small, so the force dies down very fast. If mass is larger, smaller, then this goes a little longer, and if the mass is 0, then this whole factor is 0. So e to the 0 is 1, and you go back to 1 by r. So the massless photons do give you long, and massless gravitons, if they exist, also give you this long range interaction. But the weak and interaction must be there. So a gauge symmetry now permits only rest mass 0, so it only permits long range interactions. It only permits these. Okay. Come back to our analogy of the rubber ball. So remember, the symmetry does not allow masses, gauge boson. So gauge boson mass would be like a little bit of a projection. Okay. Suppose a little bit of a pimple grew on this ball. Now, of course, if you rotate it, the symmetry is gone. Okay, you can see the rotation clear enough. So a projection would break the rotation symmetry of the elastic sphere. Similarly, a mass term would break the gauge symmetry of the universe. So what happens that if you actually raise a little bit like this in the ball, what will happen? The elastic force will simply cause it to collapse. So just as the elastic force will cause this to disappear, the gauge force will cause the mass terms to vanish. So you can't have mass terms. However, we know that weak interactions are short range. They are only seen at the nuclear scale. And the weak gauge bosons must therefore be massive. Now, if that happens, then what's going on? Is another big problem. However, the solution to this was found. Suppose you take this rubber ball and you immerse it in liquid nitrogen, fumes of liquid nitrogen. What happens after some time? The rubber ball freezes. So it undergoes a phase transition. And so the cooling in the liquid nitrogen causes the rubber to undergo a phase transition. So similarly, remember the universe after the Big Bang kept cooling. And as it cooled, it underwent a phase transition. So once that phase transition happened, the elasticity is gone. So now, if there is a projection, it can be there. So similarly, once this phase transition happened, the mass could be there. The original gauge symmetry is broken in the new phase, or the cold phase, which we are in now. And the original elasticity of the ball, of course, is also lost. Same analogy. If you go with this beautiful idea was invented by Nambu and Jonah-Lassino in 1960. Nambu has passed on, won the Nobel Prize for this idea. Jonah-Lassino, unfortunately, was not given. But let's go back to the question is that what is the analog of the rubber of the ball? What was it in the universe which underwent this phase transition? And for this, the answer was found by a set of 6 gentlemen in the same year. The first people to publish their paper were Anglais and Brout, then Peter Higgs and Guralnik, Hagen and Kibble in a few months later. Of course, in those days, remember, there was no internet, so it took a long time for papers to reach other people. So they all had the same idea independently. As it happens, the Nobel Committee decided to give the prize to Anglais and Higgs together and not the others, but that's beside the point. So what their idea was, there must be a spinless field which pervades the universe, and it is this field which underwent the phase transition as the universe cooled. This field, when that phase transition happened, it broke the electroweak symmetry and acquired a mass. The corresponding temperature, not much, only a billion Kelvin. Okay, well, that's much colder than the Big Bang. Okay, so, and of course, since then the universe has cooled a lot. It's now cooled only to 2.7 Kelvin. We know that, 2.73 Kelvin. Okay, but Higgs went further than the others. And he pointed out, you see this very nice picture of Peter Higgs, and that's the potential which he drew and the actual theory which he wrote down. So he pointed out that corresponding to this field, there will be a massive spin zero boson which can be detected through its electroweak interactions. So keep looking for it and you will find this boson. If you find it, then that's a proof the theory is correct. So this particle was called the Higgs boson. Unfortunately, the search for the Higgs boson took 48 years. So in the beginning, people had no clue to where to look for it. The mass could be anywhere between 1 GeV to 800 GeV or a little more. But over the years, as people kept searching, then this range kept shrinking. It shrank and shrank and shrank, and ultimately in 2012, the Higgs boson was discovered at 125 GeV. So we know its mass now. The machine which made this possible is the Large Hadron Collider at CERN. You see this huge machine. By the way, you can take a small cart and drive it along this thing, so that gives you an idea of the size. And this whole thing is 100 meters below the ground. But this is where, after this long 48-year search, the Higgs boson was found. And I'm showing you a picture of the meeting at which it was announced. You see the jubilation among all the scientists. And this was the director of CERN at that moment. And he's raising his hands and saying, "Gentlemen, I think we have it." So great jubilation and the completion of the Standard Model. Well, after Higgs, which the work was done in 1966, but it was followed up by work by Weinberg and Salam. And they point out that the fermions also acquire mass through the Higgs first transition. In fact, the stronger the interaction with the Higgs field, the greater the mass. So there's been a nice proof that if you plot the strength of the interaction on this side and the mass of the particle, they absolutely fall on a beautiful straight line. And that these are error bars because these are difficult to measure, but you see that they really almost all follow this beautiful straight line. And this is over many orders of magnitude, as you see, because the particle masses go over many orders of magnitude. So basically the idea is that every fermion sort of carries a lot of Higgses on its back. Okay, you remember the story, you must be remembering the story of Vikram and Vital. So just like Vikram had this Vital sitting on his back, so similarly every fermion has a bunch of Higgses sitting on its back, and the stronger the interaction, the more Higgses will cling to it. So if there are more Higgses, the particle will seem to be more heavy. If there are less Higgses, it will seem to be less heavy. The photon doesn't interact with the Higgs because the Higgs is neutral, so the photon has no mass. So it goes like that. So therefore, we have understood the origin of masses through this mechanism. Now, symmetry can also be used to understand the strong interaction because every quark carries 3 possible quantum numbers. I will explain that. These are sometimes called red, blue, and green, but they're not real red, blue, and green. They're just fanciful numbers. So the U quark, for example, there are 3 of them. And the mixing up of these quantum states does not change the physical state. So the physics doesn't change, so that's the symmetry. Mixing up of these states is called a color transformation. It doesn't change the physical state. Turns out in order to maintain this, you require 8 gauge bosons, which are also called gluons. And this gauge theory of color is called quantum chromodynamics. It's similar to the other theories. And the people who discovered it, Gell-Mann once again, okay, always there, and with his collaborators, Fritsch and Leutwiler. So Gell-Mann has passed on, of course. Fritsch and Leutwiler are still with us. They have also done many other great things. Okay, so this is the standard model we have at the end. 6 quarks, 6 leptons, 3 weak bosons, 1 photon, 8 gluons. These are the gauge bosons, 1 Higgs boson. What are the interactions? The electroweak and color are gauge theories. The color is the entire gauge part. But in addition, the Higgs has to have a self-interaction in order to give mass to itself. That phase transition will happen only if you have the Higgs as a self-interaction. And then there are the Higgs fermion interactions, which give rise to the mass of the other fermions. So these also have to be put in by extra. Of course, gravitation is not part of the standard model, but all these particles do have gravitational interactions. They have mass. And then perhaps if there is gravitation, then one day we will also discover a graviton, which we have not discovered. In addition to this, there are 2 other symmetries which the standard model does not follow, which it breaks, called parity and CP. They are technical things which I will not talk about. But you see something here, that there are all these strange ingredients. So there are the quarks and leptons, weak bosons, Higgs boson. None of them demand the other. They are all brought in and put in together. So it's like a jumble of various ideas. It works very nicely. So what it reminds me of is this house. This is a house which belongs to the richest man in India, and it's in the city where I live in Bombay. But if you look at it in the middle, it looks like several different houses, one piled on top of the other. Of course, nothing succeeds like success. So just as the person who lives here is a very successful person, the standard model has also been extraordinarily successful in explaining the results of all terrestrial experiments done so far. And in fact, here I'm showing you some numbers. This is the search for things beyond the standard model. This is 1 TeV, so 1000 GeV. And this is where the Higgs mass is. This is 1000 GeV, and you already see that most of the space has got filled up. That means nothing has been found. Only the white space is left to find. Well, does that mean that we have a complete theory of fundamental interactions, particles and the interactions? So can I close the talk and go home? Answer is no. And why not? That is because of certain problems which are still there. And these you will hear more about in the other talks, but I'll quickly explain it to you. But first, a little bit of a flashback. In 1890, wrote, it seems probable that most of the grand underlying principles have been firmly established, and that further advances are to be sought chiefly in the rigorous application of these principles to all the phenomena which come under notice. An eminent physicist remarked that the future truths of physical science are to be looked for in the sixth place of decimals. So in 1894, he thought that everything had been discovered. We had the final theory, which was electromagnetic theory, and there was nothing much to be done except precision measurements. Of course, he was proved completely wrong, because in a few years after that came quantum theory, quantum mechanics, relativity, special relativity, general relativity, the entire electronics revolution, computer revolution. So much has happened since that time. So it's not good to be complacent. Surprisingly, another great scientist, okay, like Millikan was also a great scientist. You see here a picture of Stephen Hawking. I've deliberately shown you a picture of Hawking when he was not unwell, when he was fit, but in 1993, which is about 100 years after Millikan, he wrote, although we have not found the exact form of the physical laws, we already know enough to determine what happens in all but the most extreme situations. And then he says we gave it a 50-50 chance that we will find the exact laws in the next 20 years. So 20 years have gone by since 1993. We have not found the exact laws. We are still with the standard model. So maybe this is a phenomenon which repeats every 100 years, like pandemics. So it's possible that we will find more, but it's good not to be complacent. And there's good reason for that, because there are many puzzles. You will hear much more about this later. So the first one is the dark matter puzzle. This is a picture of the sort of universe. So every galaxy you see seems to be immersed in a halo of dark matter. Now, this is only a computer-generated plot. The dark matter is actually dark. You can't see it. This is what you really see. So most galaxies and the dark matter seems to have only gravitational and possibly weak interactions. Now, if that happens, of course, there are in fact some galaxies. This is a galaxy called the Dragonfly 44 galaxy, which seems to be 99.9% dark matter. Again, this is you only see the darkness here. You don't see this. The standard model has no particles which can explain dark matter. So that's the question. People have been looking for them. There are these experiments made, and which beautiful experiments where you take a tank of xenon, liquid xenon, and if there's a dark matter particle which will come, it will interact with those. Electrons will come and interact with the detectors here. Unfortunately, there's been no success so far. So that's a big question. We don't know what dark matter is. There is also the idea of dark energy. What is that? We know that the universe started with the Big Bang. So there was an explosion, there was a fireball which expanded and kept expanding. After some time, it started cooling, and as it cooled, it condensed into filaments, and those filaments eventually condensed into galaxies and stars and planets, and that's where we come from. Okay. However, that's our picture of the universe. However, you see that as the universe expanded, there's a radius parameter you could think of, and this radius has kept increasing. Now, Edwin Hubble in 1929 showed that the rate of increase of this is proportional to the rate itself. So it's a logarithmic growth, and the rate is a constant. The rate of growth is a constant, which is known as Hubble's constant. However, in the end of the last century, that is towards the end of the 1990s, it was shown by these three gentlemen, Perlmutter, Schmidt, and Rice, that actually the rate is greater than expected by the Hubble expansion. The expansion is actually accelerating. So this straight line, this blue line, shows you the Hubble rate. And you see that as you go further away, the rate seems to be a little faster. So it's actually greater than this. Now, to understand this, it will require some matter which, instead of attracting as gravity does, it should repel. So matter with a mutual repulsion is not known. There's just a name for it. We call it dark energy. And of course, the standard model has no particles which can explain dark energy. So that's another big question. Then there is the question of antimatter. In the aftermath of the Big Bang, radiation converted to matter. Okay, and of course, how much matter? We know that by the famous equation equal to mc squared. The radiation became matter. Now, the basic standard model interactions for these conversion essentially don't distinguish between particles and antiparticles. So you should have produced as many particles as antiparticles. But of course, we didn't. The universe is composed only of matter. Where are the where is the antiparticles? Where is the antimatter? So this was pointed out by Sakharov. A.D. Sakharov in 1967 showed that weak interactions have a small particle antiparticle asymmetry called CP violation, This is what was, I'll come back to that in a moment. So he said that this CP violation must be responsible for this asymmetry between matter and antimatter. And remember that Kobayashi and Maskawa had said that CP violation can be included in the standard model if there are 3 generations. There are indeed 3 generations. So that's how the CP violation must be coming. So this has been brilliantly proved by the Bebar and Bell experiments between 1998 to 2004. So they have actually measured something like about 10 to the minus 7% difference between the matter and antimatter connections. So that amount of matter-antimatter asymmetry is there. But can it explain the universe? No. This is only 10 to the minus 7%. And what you should have is about 100%, right? Because there is no antimatter. Lots of matter, no antimatter. So where does all the CP violation come from? We don't know. Then there is something called the mass hierarchy problem. I'm running out of time, so I'll just go through it fast. A free or non-interacting Higgs, if we just had a Higgs boson, it would travel like a classical particle. It would go in a straight line at a constant speed and just make it go to and fro, but it would be the same. However, if it has interactions, then in a quantum theory, it can pull particle-antiparticle pairs out of the vacuum and basically grow by having the mass of those added to it. So as the Higgs travels, it will become more and more mass. It will become heavier and heavier, and within a very short time, very, very short time, the Higgs is going to become very heavy, very, very heavy, very, very massive. So where does it stop? Can it go on acquiring mass forever? No. It will stop when the Higgs boson has become as heavy as the heaviest particles in the theory. Which are those? Where will those happen? Those will happen when the gravitational interactions become as strong as the electromagnetic interaction. That's at a mass called the Planck mass. Where is that? Gravitational interactions are much weaker than the electromagnetic interactions. So you have to really take the mass up very high. And that's the mass. It is a billion, 19.2 times of a billion, 19.2 billion GeV. But the Higgs mass is only 125 GeV. So it's so small compared to this huge mass. So what's going on? How is that possible? This is also something we don't understand. Finally, there is the issue of whether this vacuum is stable or not. I'll come to that. See the potential energy due to the Higgs boson. You saw a little picture of that in Higgs's picture, but it changes shape as you go to higher and higher energies. So let's do that. Let's plot energy along this line, and let's plot the potential here. So this is how the potential looks now. Okay, it has a peak in the middle, and so we are somewhere here. Well, this is actually 3-dimensional, so it could be somewhere here. So we are, let us say, here. But when you take the energy higher, then the potential becomes deeper. If you take it even higher, it becomes deeper and deeper and deeper. And this is again going up still. But when you take it to a certain value, the potential simply goes down to minus infinity. So at this point, the vacuum becomes unstable. And that means that if you place a particle anywhere, suppose for example there's a particle here, this is where we are now, it could simply go down to minus infinity, emitting an infinite amount of charge. If there is no minimal energy, particles can go down to minus infinity energy, emitting infinite amount of energy, and that's what we call a catastrophe, because it means the universe is going to burn up with a huge flash of energy. Now this does not happen, okay? And because after all, during the Big Bang, the energy of the particles was much more than this. And if there was so much energy available at that time, it would never have cooled. The fact that the universe is cooled tells us that there is something wrong. So there is something here. We have used the standard model perfectly. So there must be something beyond the standard model to explain this. Again, one more question. So lots of fodder for thought, things to be thought of, and it's not that theorists have not thought about these. People have thought a lot about these in the last 50 years or so, and have come up with many ideas. So this is a slide I have stolen from this blog, and it sort of shows you the kind of scenario. There are many ideas, different ideas of different kinds, spontaneous CP and this and that, so MSSM, supersymmetry, and other things. And of course, there are many things which are not thought of yet. Of course, people are all still thinking, and we will perhaps find more things. So there is a lot of things still unknown to us. We have found many things, true, So I can think of nothing more fitting to end this talk with than the famous quotation from Isaac Newton. You know what he said: "I do not know what I may appear to the world, but to myself I seem to have been only like a boy playing by the seashore, like this fellow here, and diverting myself and now and then finding a smoother pebble or a prettier shell than ordinary, while the great ocean of truth lay all undiscovered before me." So since Newton's time, we have found some more pebbles, some more shells, but perhaps the truth lies undiscovered, and some of you young people, perhaps you will work in this area and wade into the sea and find more things. So thank you for your attention, and I hope you enjoyed the talk.
Thank you, Professor Raychaudhuri, for such a nice talk. And we could see a few questions, and we have a couple of minutes in hand before the next talk. So can we quickly, may I tell you, or you will pick up the questions from the chat box? It's there. You can pick up.
I can't see the chat box, so it would be good if you could just quickly read them out to me, or the person who could ask it again.
Yeah, sure. So the first question was asked by Devajyoti Vallabh, who is asking, does gauge symmetry predict about the existence of graviton? That was his question.
Well, the answer is both yes and no, in the sense that the gauge symmetries I have shown you, the gauge symmetries for the electroweak and strong interactions have nothing to do with gravitation. But yes, you can write down gravity itself, which is the general theory of relativity. You can write it down as a gauge theory, but only in the limit when the field is weak. When the field is strong, for example, near a black hole, you cannot write down a gauge theory. So that is something we don't understand. But yes, if it is a weak field, as it is near the Earth, then you can write it down as a gauge theory, and that gauge theory will predict graviton, yes.
So I hope.
So the answer is yes for weak fields, no for strong fields.
Yeah. So next question asked by Arnav Vishal. The phase transition of our universe, which actually nothing else than Fichte violation, can this phenomenon be studied with the framework of newcomer theory of quantum phase transition? What he wanted to? Okay.
Well, the answer is, again, mostly the answer is no. But there have recently been ideas of trying to explain gravitation itself as a statistical phenomenon, which is called something called an emergent force. If you, though, in those theories, perhaps you could think of the graviton as something dealing with the quantum phase transition. But on the whole, I think if we stick to Einstein's theory, then answer is no.
So I think Arnav, yeah. So Archana asks a basic question. So it's do the gluons acquire mass through Higgs boson phase transition? I mean, they were asking.
The gluons.
Yeah.
The gluons do not acquire mass because the Higgs boson is only weakly interacting. It doesn't have strong interactions. So it doesn't interact with the gluons. Result is the gluons remain massless.
So one more question where the participant asks that he has a doubt. All this began when the structure of energy were being reinterpreted as information. So isn't it ultimately the expectation to have a collection of all the structures topologically structured with energy, where different structures define different properties and possible ways of understanding them? So he wants to interpret as the information, quantum information and topological structure.
Well, all knowledge is information, but I don't think you can interpret energy as information. Okay, I don't think that's going to work. Quantum information is a different idea. It has to do with entangled states, and here we are looking at essentially asymptotically free states, states which are far away and free. So we are not. I don't think we are looking at entangled states here at all. So that's a different phenomenon, and it doesn't apply here. So the answer is no. Answer to your question is no.
Yeah. So
any other questions?
The few questions, and somebody is asking what is a virtual particle and why do we need them? What is meant by a virtual particle? Yeah. So.
Yes. So this is a rather technical question.
Yeah.
So the point is that that's the way we think in quantum mechanics. In quantum mechanics, you see every state has a bit of all the other states put into it. There is something called the completeness hypothesis, which tells you that if you deform a state by a little bit, then whatever deformation can actually be thought of as a combination of all the other states coming in. So the result is that if you have that's what I said for the Higgs boson. If it is non-interacting, then it is just one state. It's like an eigenstate. It remains as it is. But if you deform it a little bit, if you displace it a little bit by having interactions, then that particular state will have all the other possible states coming into it because of the completeness of quantum mechanics. It's a little bizarre to understand in classical terms, but that's the way quantum mechanics is. So all those are other states which come into the state. That other states coming into it are the virtual particles. That's the way to understand quantum field theory. When you are studying quantum field theory, you will understand this better. But this is the best way I can explain it at the moment.
Yeah, Ramana, I think you have to, I mean, I don't know your background, but possibly, yeah, you need to go to quantum field theory a little bit about it to get the full picture.
Yes.
And I think we'll have to stop here today because our next speaker, Professor Gopakumar, is waiting. I'm just closing this session. I'm closing the